Let's begin with chapter 4. The topic of chapter 4 is about the board kinematics. Board kinematics is core part in robotics research. Actually, in traditional case, the DH notation, Danabi-Hartenberg notation is used to derive a homogeneous transform ultimately for the board kinematics. In this chapter, we will introduce the POE concept, product of matrix exponential. Actually, it makes the big difference between this modern robotics and the robotics related to other textbook. So I'd like to recommend you to learn in depth and in detail the product of matrix exponential. Okay, the board kinematics is related to calculation of position and orientation of each end-effector. Okay, so this is the fixed coordinate. This is the end-effector frame here. Okay, the target is to calculate this position and orientation. So by using the trigonometry, we can write down the x directional component and the y directional component. Like this is the L1 cosine theta 1. This is L2 cosine theta 1 plus theta 2 because this is the theta 1, this is the theta 2. Like this, we can write down the x position of end effector. On the other hand, the height will be the sine component. So by adding 3 components, we can get the y axis value. And then orientation will be the addition of all possible orientation. So we can get the orientation. Like this, Cartesian position and orientation will be the function of joint angle. Okay, this procedure will be derived in a systematic way. As mentioned before, this will be called as product of a matrix exponential. Okay, the first step, let's assume all the joint coordinates are 0. So this is the fixed base, the first link, and the second joint, second link here, third joint, third link here. And then the end effector frame will appear like this. As you can see, this is the x-axis, this is the y-axis. Let's lead to this position of end effector frame. So the position will be the L1 plus L2 plus L3 as an x component, and the y and the 0 will be 0. Z-axis values will be 0. And then the orientation is the same with the fixed coordinates. So we have the identity matrix 3, 0, and 1. It can be obtained by reading the end effector frame in terms of base coordinate, base frame, fixed frame. This is the first step, and let's take the second step. The theta 3, the rightmost joint is movable. Theta 3 is not 0, but other 2 joint angles are zeros. Those are assumptions. This is the fixed coordinate, link 1 and the link 2 and the link 3. Joint 3 can be movable, so this will be the theta 3, non-zero. Okay, maybe this is the end effector frame. By letting this concept, and then let's obtain the square axis. corresponding to rotation about 3. Okay. Let's obtain the omega 3 first. How about that? This is the x-axis, this is the y-axis, and then out of phase direction will be the g, this is the z-axis. So the omega 3 is equal to 0, 0, 1, is it right? The axis is directed to the out of phase. So if you make this kind of a rotational movement, at that time the linear velocity of end base frame will move like this. Okay, in this case, we can assume that this is the rotating turntable. If you make the rotational motion like this, at that time this position will move, will make the linear velocity like this. This will be the P3. The length is the L1 plus L2, and then direction is minus y. So in minus y direction, the magnitude will be the L1 plus L2. Is it right? So like this, we can write down the square axis about the joint 3. It can be applied to joint angle 2 and the joint angle 1. Okay, the square axis joint axis S3 can be taken as a SE3 matrix form. Okay, the supersymmetric matrix form of omega 3 and the linear 3 vector. So we can write down the R 4x4 matrix. Okay, it's very easy to obtain the matrix form of square axis. And then let's take the matrix exponential representation for square motion. Okay, E2 S3 theta 3 will be the R 4x4. Okay. According to the Rodriguez formula, we can get this equation. So omega 3, 2 times of omega 3 matrix is this one. It's not difficult, just by multiplying same matrix we can get this one. Okay, according to the Rodriguez formula, we can get this rotation matrix. In previous lectures, we have derived this G matrix. Okay, so applying this kind of parameters, we can get this equation matrix. Let's apply the V here. The X component is 0, G component is 0, so the second column will appear with the multiplier, this one. So that will appear, like this. So we can make the homogeneous transform from the matrix form of square axis. Okay, for given 0 matrix, for given 0 position, okay, pre-multiplying some homogeneous transform is maintained in the same base frame. We have talked about it in the previous lecture. So let's apply the matrix exponential form, and then this one will rotate or translate about this M matrix. So by multiplying both sides, we can get the rotation and the translation. Actually, it is corresponding to base 0, 0, and movable third joint. This is the x-axis, this is the y-axis, and the effector prime is here. Okay, so this angle is a theta 3. So rotation matrix will be this one. How about the position? L1 plus, L2 plus, L3 cosine, and L3 sine. So like this, we can get the component, x component and y component. Okay, going forward, okay, theta 1 is 0, but theta 2 and theta 3 can be movable. At that time, from the previous derivation, we will apply the one more homogeneous transformation, or matrix exponential, and it will make this matrix will translate and rotate it. Okay, so for these formulations, we should derive the square axis. Square axis is about this one. So square axis will be the very similar way. The omega is the same. This kind of omega 2 at that time minus y direction linear velocity will appear in the origin of base coordinate, so we can get it. Okay, and then we will apply the remaining first matrix exponential or homogeneous transformation by using the square axis like this. Then we can get the generalized homogeneous transformation from the base coordinate to the end vector frame. Okay, let me read you the several comments about the Bode kinematics. Bode kinematics can be expressed as a product of matrix exponential, in short, POE. This is the core of this chapter, each corresponding to the square motion. Okay, the first step is to derive the square axis, and then we take the matrix exponential. Then this matrix exponential will be applied to the as a pre-multiplication form to the zero position. Okay, the POE derivation of the Bode kinematics does not use any link frame. Actually, if we wanted to use DH notation at that time, every joint and link frames are required to derive the Bode kinematics. Okay, here another representation of the Bode kinematics of open chain relies on Danabi-Hartmann parameters. If you wanted to learn more detail about the TH notation, you can you can get some advice from the appendix part. Okay, the advantage of DH notation, it requires the minimum number of parameters. It makes the computation efficiently to derive the robot kinematics. For example, for n-joint robot system, 3n numbers is required to describe the robot structure, and numbers are required to describe joint variable. This for n numbers will be the minimum to describe the kinematic structure and the variable. On the other hand, the POE representation is not minimal. Actually, it requires 6n numbers to describe the n square axis. One more, the n dependent joint variables are required. So this is not minimal, but POE does not require any link frame or joint frame. So there is a trade-off between both. Okay, let's go to the section 4.1, POE formula. Okay, in order to apply the POE formula, we will we will assign the base coordinate denoted by the S, and then link, joint. Anyway, the last will be the end vector frame. This will be denoted by the body frame B. Okay, so in many cases, the zero frame will be equal to each other, and this is the first. Okay, this is if you add the joint here, maybe the joint will make some movement. The movable frame will be denoted by the 1, 2, blah blah blah. This is the n. The last part will be the n plus 1. So n plus 1 will be assigned to the body frame. So the fixed frame will be the zero axis, zero frame. N plus 1 frame. Sometimes it can be the body frame. Sometimes it can be the in some case this can be neglected, ignored, because this is not required sometimes. Okay, the first formulation is about the square axis in the base frame. Actually, it has the short name, space form of the POE. Okay, let's consider this is the fixed coordinate as end effector frame. See here, this is denoted by the P. Okay, to consider the general special chain, open chain. Okay, here this robot system has an wound-up joint. Okay, the joint is all the time connecting the two link, not three link, just the two link connecting. To solve the board kinematics, we must choose the fixed base frame first, and then end effector frame be attached to the last link, and then place the robot in its zero position by setting the old joint as a zero, like this, with the direction of positive displacement should be satisfied for the joint. The first step, let's obtain the M, the configuration of the end effector frame relative to the fixed frame when the robot is in its zero position. Okay, so M will be called configuration at the zero position of the robot. Okay. In here, this is a 0, this is a 0, this is a 0, and this is 0. And if you read this reference frame in terms of the S, that will be the M. Okay. Suppose that joint N is displaced to some joint angles at the N. Then the end effector frame M will be undergoes a displacement of the form. Okay, the last link is move like this. At that time, we can find out the square axis, and then we make the matrix exponential using the square axis. That will be applied to the as a pre-multiplication of M. Okay, this will make the translational motion and the rotational motion about the M matrix. Continuing with this region and now allowing all the joint to vary as a pre-multiplication. This is the POE, product of a matrix exponential formula describing the Ford kinematics of n degree of freedom open chain. Okay, it is called space form of the POE. Okay, in short. Okay. In here, every coordinate, all the square axis will be expressed in the fixed space frame. Okay. Okay, let's summarize. To calculate Ford kinematics, using the space form of the POE, we need following element. First one, end effector configuration M should be specified when the robot is at home position or zero position. I prefer to use the zero position because it is more intuitive to describe the robot posture. The second, the square axis from S1 to Sn expressed in the fixed coordinate. Those are core elements in describing the board kinematics. And then we will take the matrix exponential using the square axis. And then it will be multiplied. It will be pre-multiplied of the matrix M. Then we can get the final homogeneous transform. Then we can know that the orientation of end effector and then position of end effector. Last one, joint variable will be applied as a variable. Okay, let's take an example. Okay, here, this is the base frame. This is the end effector frame. Okay, so we have the three joint variables. This is the first joint variable, second, and third. So it will make the 3 degree of freedom in special case. Okay, maybe the pole kinematics is obtained like this. In here, the M and S1 and S2 and S3 value are required. Okay, so let's obtain the M. Okay, let's lead the x-axis and the effector axis is corresponding to this one, so 0, 0, minus 1. Y-axis is equal to the y. The same, 0, 1, 0. Z2 will be the x, so 1, 0, 0. And then let's lead the position of end effector. Okay, the x-axis will be the L1. L1. There is no y directional component, y. G will be the minus L2. And then 3, 0, and the 1 is required to make the homogeneous transform. Okay, like this we can make it. One more, let's add the square axis of this robot system. Okay, let's obtain S1. Okay, here the rotation axis is the G direction, so we have 0, 0, 1. And then let's take the linear velocity according to the movement of the zeta 1. Okay, let's apply this rotation motion to here. At that time, actually this is the same position, so there is no distance between both, so that will be equal to the 0 linear velocity. Okay, S2. Okay, here the rotational movement of this part will be the minus y0, so 0, 0, minus, 0, minus 1. Okay, minus y direction, so 0, minus 1, 0. Okay, if you apply the rotational motion of this one, then this position will move like this, minus g direction with the unit of the L1. So 0, 0, minus L1. S3. S3 is corresponding to this movement, so it will be equal to, it is aligned to x-axis, so 1, 0, 0. Okay, here, Okay. This x directional rotation motion is applied. At that time, minus y directional movement will appear at the origin. So with the unit of L1, L2, right? So 0 minus L2, 0. So this is listed as a table here, and here, and here, and here, and here. So we can get, after getting the square axis and the final configuration, the zero configuration of the M, by applying this kind of data to the POE, then we can get the Ford kinematics. Okay, this is more simple. Okay, this part is equal to this one, and then the origin will be post frame is assigned to the end-effector frame. So this will be the B. So we have just the three angle, theta 1 and the theta 2 and theta 3, so we can get the Ford kinematics. Let's lead the zero position, maybe this and this and here. So okay, too many joint. Okay, you're right. That's right. Okay, so we can lead this position. So X, Y, and Z. Orientation is the identity. So we can get the zero position computation like this. Let's lead. Okay. Actually, this rotational movement will make the. This is the first. This rotational movement, there is no linear velocity, so 0, 0, 0. Okay, so second joint is rotated like this. At that time, minus L1 y directions will appear here, and minus y direction with the magnitude of the L1 plus L2. So we have this linear velocity. Okay, if you combine this kind of phenomena in the planar case, at that time, just the three vectors corresponding to omega z, Vx, and Vy will be required to describe the planar motion. So the Ford kinematics is the same, but the M matrix, dimension of the M matrix will be reduced to the R3 times 3. Okay, so this rotation matrix is the identity, 2x2 identity matrix. And then the X component, L1 plus L2 plus L3, Y is the 0. In here, square axis, the direction will be denoted by the omega, so all the component will be the 1. Omega z appears 1 in this robot system. The Vi, the linear component, the first one is 0, minus L1 plus L2 will appear to describe